No? Oh, okay. I spiked myself. All right. So, good evening. Last presentation. And as we've seen, we've been looking at what liquid jets do, how they form droplets, what controls the droplets, and all that. But my presentation is going to be all about what happens once the droplets have gone, vaporized. And with what you're left, with is just unsteady, is just a flow with unsteady fuel-air ratio stratification. So the motivation for doing this work is combustion instability, which is very familiar to everybody who works with gas turbines. And the main driving mechanism for combustion instabilities is coupling between acoustic modes and say other heat release response in a combustor. So let's say we have a cartoon of a gas turbine combustor here, and we have a fuel injector here that's putting a spray out that's vaporizing completely, and eventually you have a flame that is completely sitting in a gas phase flow, a single phase flow, but with fuel and air. Now, if we have acoustic perturbations in this system, we could get, as we've seen, changes in atomization characteristics, changes in droplet size distributions. We could get clustering and basically all kinds of effects, which can then lead to this pre-vaporized stream becoming stratified in an unsteady manner. And when you have unsteady fuel-air ratio stratification coupling with a flame, you get heat release fluctuations, which then drive, which acts as a driving mechanism for pressure fluctuations. So this is a paper I found when I was looking for pictures on how say droplets would behave under forcing. And this is a this was from a paper by Wark, and he had his setups shown here as a schematic, and he's basically got a methanol spray down here, which he forces with a speaker. And what you're seeing here is a picture of the spray as it comes out of this contraction at this point. And you see that because of forcing, you get these nice regular structures, which you don't see in the unforced spray. And mostly you also get these clusters of droplets that break off from the main spray as you go downstream. And so when this happens, I would assume that this kind of clustering would now influence evaporation rates of the droplets. And so when this thing, assuming it had sufficient residence time before it hit the flame, would result in, say, a locally fuel-rich region or a fuel-lean region, depending on how the clustering happened. So when you have such fuel-air ratio stratification, you get heat release oscillations by various fundamental processes. So if you have equivalence ratio perturbations, you get perturbations in local heat of reaction of the mixture. You get perturbations in the local flame speed along the flame. And that would directly result in heat release oscillations, as you can see from this little formula that I've put here, which is basically the integral of the local heat release rate over the flame. But because you get flame speed oscillations, you also get flame speed oscillations along the flame. You get now different parts of the flame regressing into the upstream flow at different rates. So this causes the flame surface to wrinkle, causing the burning area of the flame to oscillate. And that gives you an additional mechanism for heat release oscillations. So how do we model this? We've developed a whole sequence of models applied to various thin flames, various simple flames. And what I'm going to do in the next few slides is kind of generalize it and put it in a general setting so that it can be applied to just make the case that it can be applied to complex flames in general. So we assume that the flame is a thin boundary between reactants and products. This is fairly well known and well established now at even gas turbine conditions. And for what I'm going to show in this presentation, the flow will be assumed to be uniform and parallel along this y-axis, and we'll neglect the influence of gas expansion at the flame. So what this basically means is the flame sees the flow, and whatever there is in in the flow, but the flow itself doesn't get affected by the flame. So in a sense, it's a one-way coupled model. And this makes the mathematics sufficiently simple so that at times we can even get analytical solutions, which would then be needed for using in things like active control and other applications. So if we assume that the flame is a thin surface, we can track it as an interface, so which naturally lends itself to treatment with level set methods. And and the rest of it is pretty routine. You solve it using a local level set method, and you can compute heat release. You can compute the heat release response in this fashion by just doing this surface integral of the heat release over the flame using level set calculus. And sure, this can be applied to simulate fairly complex configurations, and it can also be and very complex flow situations as well. So you can do stratified flames, because all you have to do then is make your SL a function of the local equivalence ratio upstream of the flame, as I will show you in this work. We can also do turbulent flames in general. It's well known that level set methods can capture really complicated surface changes and all that. And this is an example from I wouldn't call this a turbulent flame, but something that was used to understand some physics of turbulent combustion. And this whole model, and using this approach, we did a theoretical analysis for Bunsen flames. And that can be found in this paper, where we analyzed basically the various pathways by which flame heat release can oscillate, and when these things become important in when you vary frequency, etc. And this is now a typical result from that model. And what we found basically is that the heat release response magnitudes scale with the sensitivities of flame speed and heat of reaction to equivalence ratio, as isn't very surprising. And we looked at rich flames also, because at the time when we did this work, there was some interest in looking at running gas turbines in partial oxidation mode, so as to get syngas out at the other end, and then run it through, say, a water gas shift and do carbon capture and storage for those kind of applications. And what we find is, since for rich flames, the heat of reaction is not sensitive to equivalence ratio fluctuations, the low frequency response is 0, unless you have something like velocity fluctuation. So this is a very interesting difference between rich and lean flames when they're forced only by equivalence ratio perturbations. So now, but what wasn't done back then was comparing this with some kind of detailed simulation to see how well this model can actually do quantitatively. So in order to do that, we did I've done this simulation of a 2D premixed methane air flame, whose inlet methane mass fraction is harmonically forced. And I keep the total mass flow rate constant. Now this might raise a few eyebrows, because that is fairly synthetic, but the aim is to make sure that I don't introduce velocity perturbations into the flow by letting the mass flow rate oscillate. And so I can just extract what the flame does only when it sees a equivalence ratio perturbation. And so that allows me then to just validate that particular mechanism for heat release response. And I did the whole thing with a simple one-step global chemistry, which in the papers I show can capture the flame speed when you compare the predictions with GRI and other experiments. And so the way I model this flame is I choose a nominal baseline level set shape shown like this. It's chosen to correspond as closely as possible to the this temperature contour, 390 Kelvin. Because I do that because the SL I put into the model is the unburnt SL. So you want to make sure that the flame shape that you're tracking corresponds as far as possible to the upstream boundary of the flame in the DNS. And the phi field I determine from just solving transport equations. So this can, within the reduced order within the framework of the reduced order model, since the flame isn't actually seeing the flow, this is very easy to do. I mean, in the computations that I did here, I've done this with a second order scheme with first order Euler time stepping, and as I'll show that this actually can pick up this field in the DNS pretty well. So this is how the flame looks in the DNS. Upstream, you see the field upstream basically shows the local equivalence ratio perturbation. And this thick boundary here is the 390 Kelvin contour. And the thin curves are basically reaction rate contours. And you can see that as these striations pass through the flame kind of burns in at locally rich regions and kind of gets pushed out at the lean regions, giving this kind of wavy, wrinkly structure. And for this particular forcing amplitude, which is about 14%, I don't have this on this, but it was 14% of the mean equivalence ratio. And you see that you even get these nonlinear topological change events with that thing breaking off at the tip. Now, before I launch into comparison between flame response, we need to make sure that our equivalence ratio field is similarly captured between the reduced order model and the DNS. That's when, because only then can we say we've done an unambiguous comparison. So this is a plot of equivalence of the phase of the magnitude and the phase of equivalence ratio perturbations at various axial locations as a function of transverse distance. So basically at 3 different points, at the slot end somewhere here and somewhere around here, I just look at the variation in magnitude and phase along x. And you can see that it's pretty one-dimensional. And this is true for almost all cases, all the cases that I simulated. And this is a comparison for the axial variation of the magnitude of equivalence ratio fluctuations. The symbols are from the DNS, and the curves that you see are basically the reduced order model, basically determined from from solving the transport equations. And you see that I pretty much nail it. There's no so the upstream. So both the reduced order model and the DNS are seeing the same nominal upstream oscillating equivalence ratio field. So how do the describing functions look? So I just quantify the heat release response as describing functions. You don't have to do it this way. You could get a Q of t time series if you wanted, because the model is in general set up to work in the time domain. But I just put it up. I just present the results as frequency domain results because it can be done compactly and discussed, etc. So you get this. So you can see that you seem to get some kind of agreement at low frequencies in both the heat release. This is the heat release, and this is just the burning area component of the heat release. And you see at low frequencies you get this kind of agreement. And this high frequency region as well, as I discuss in this paper, can be explained because of the slight geometric differences between the baseline flame shapes in the DNS and the reduced order model. But what those arguments can't explain is what happens here in the middle. So why do we get this large overshoot, especially? And the reason for this is, in this particular case, is the Darius-Landau instability. Now, just to remind everybody what this is, this happens because you have gas expansion at the flame surface. So if this blue vector represents the flow velocity going through the flame, and this green vector represents the normal component, we know that to leading order, the normal component accelerates, whereas the tangential component just goes through unchanged. So because of that, your streamlines kind of distort in this fashion. And since you have constriction of streamlines here and kind of dilation of streamlines there, you get flow acceleration and deceleration upstream of the flame, which then promotes. If your nominal flame speed were to be constant, it would just cause these wrinkles to go on expanding, increasing in amplitude rather. And when this happens, you start to create flame area, so you increase your burning area, and hence you increase your heat release response magnitude. what happens, but what I have is not a flat flame for which is the classical canonical Darius-Landau case. But what happens is actually this was first shown, I think, to my knowledge, by Searby's group, where they took a slot flame like this and put a rod somewhere at the base and oscillated the rod in and out of the flame, creating perturbations just right there at the base. And what you see is this nice amplification of perturbations. The upstream flow here is steady. There's no forcing. And you see that these perturbations just grow as you go from base to tip. So basically what the tangential velocity to the flame surface does is takes what is actually a temporally unstable situation and converts it to being convectively unstable. So I just call this thing convective Darius-Landau instability. And this is what is happening in the DNS as well. You can see that from this movie here, which is plotted for this point, which I've shown for this what the flame's doing at this point. And the field shows as the transverse velocity component, the instantaneous transverse velocity component. And you can see that whenever I get this kind of concave bulge toward reactants, I get an upstream flow acceleration, which is what the DL instability theory tells you, right? And plotted, and what the black curve that you're seeing on that is actually the corresponding result from the ROM. And you can see that the ROM hardly is doing anything compared to what the DNS is doing. So that clearly explains why there's this massive difference between the two. So this is, and I just wanted to quantify this as well, just to make sure it wasn't a one-off thing with a movie. So I took two Struhal numbers, one really small, which is the black, and one which is really large, about 400 hertz, which is the green. And you see that for both cases, the symbols and the curve, for both the black and the green, they're fairly close to each other. Whereas for the red, which is that point where you had the maximum difference in predicted amplitudes, you get a massive difference between what the DNS does and what the reduced order model that neglects gas expansion gives you. So clearly this is happening because of gas expansion effects and the resulting flame front instability. So to summarize, we can get unsteady fuel air ratio stratification in gas turbine combustors because you have interactions of acoustic waves with sprays and maybe air inlets, which then causes influences the local mixing. And a comparison between my reduced order modeling and the DNS suggested that neglecting gas expansion works in some cases, which is good news. But the bad news is it won't work everywhere. Okay, so with that, I move on to the outlook, and this is, I think, the next most important problem that has to be addressed. We need to look at all I looked at was or all that the comparison that I showed before this slide was basically living down here. So let me just orient you guys on this plot. So this is a regime diagram where I have perturbation velocity, the amplitude of the perturbation velocity, and the forcing frequency here from Bayau's group. And this was essentially for a Bunsen flame which was forced acoustically from the upstream side. And you can see that they observed for various combinations of perturbation velocity, perturbation amplitude and frequency, they observed various kinds of flame behavior. And the reduced order model pretty much lives here. This is what you could predict if you completely neglect gas expansion effects. You wouldn't be able to predict anything else. Okay, and there have been several very nice experiments from IIT Madras that have shown that you can get flames in self-excited combustors that show all these features, all these various features. So clearly neglecting flame front instability effects in the heat release model is not going to take you towards quantitative predictions of combustion instability. Okay, then the next thing you need to do is get a good model for the upstream flow feed. What I did the comparison for was to use a uniform parallel flow, which is great for this kind of theoretical analysis, like looking at these academic configurations. But in a real combustor, which is with swirl, you get these unsteady structures. For example, this is a picture from this paper by Shanwu Wang, and it's essentially a non-reacting swirling visualization of the precessing vortex core in a non-reacting swirling combustor. And this PVC, there have been several reviews on this phenomenon, and you can see that this PVC is dependent. When this PVC appears depends on flow conditions. You never always get a PVC. You sometimes get it, you sometimes don't. But we don't know for certain with any degree of certainty. We can't predict it using a reduced order model, and that's got to be addressed before we can move towards quantitative predictions. And finally, what happens? I did the whole thing for this level set method. Everything works when you have an unbroken flame. So the validation, the results that I showed you were for a nominal mean equals ratio of 0.85. But what if you go towards low NOx operation, where you have a mean equals ratio of 0.6 maybe, or even lower, 0.52, 0.53. So in such a case, this is a result that I presented at Atlanta earlier this year, and this is essentially a slot flame, which is again forced with a mean equals ratio of 0.6, which is being forced with an amplitude that is about 60% of the mean. So clearly, and the left half essentially shows the instantaneous phi as a offset from the steady flammability limit. So you can see all the blue regions are where the mixture is locally non-flammable in a static sense, in a nominal sense. And you can see that even corresponding to these blue regions, you get these holes that are forming. And these holes, these contours represent basically consumption rates of methane. So you can see that there are breaks in the methane consumption. Now, how would you model this within a reduced order model? I'm not entirely sure yet. So I think these are basically the outstanding questions that, as far as I can see, we should address first before, which I'm sure will yield more cans of worms as you go into them. So I think I'm going to leave you guys with that.
Thank you, Dr. Hemachandra. We are having time to take a couple of questions.
Actually, if you look at the premixed flame is basically kinetically controlled. Okay. And in your model, you have taken a single step chemistry and where you are changing your equivalence ratio by 60%.
No, not for this one.
Or is it 14%?
No, that was 14%.
14%. So how you will, take care of that aspect in predicting certain things, because all these things will be changing. Activation energy and pre-exponential factor and other coefficients.
Yeah, so what basically controls the heat release response here is the effective flame speed. And if you see, and what you're talking about non-quasi-steady effects, which means, so what I assume in the model is the SL is essentially the SL is the quasi-steady SL for the local equivalence ratio.
See, SL will be coming from the heat release, right? Integration of the heat release.
No, SL is just a correlation in the model.
You are using correlation. Okay.
Yeah, SL versus phi.
Then that doesn't matter.
Which correlation I get from an analysis of
and
SL
which will
from
be
this model.
function of equivalence ratio, right?
Sure, sure.
Okay.
Absolutely.
I was thinking you were getting the burning velocity from the heat release itself.
No.
Generally,
Not in the reduced order model. In the DNS, of course, it comes from whatever chemistry I assume.
but is it you are using DNS full kinetics,
Yeah.
multi-step combustion kinetics?
No, the kinetics in the DNS for the validation study I did was single step.
That is my concern.
But that has been shown to predict things well. Gonim's group they've done it for forced flames with things. So as long as you don't hit frequencies that are so high that you start hitting some Karlovitz number that of one of the internal reaction zone reactions, you should be okay. Essentially, your external forcing is of a sufficiently slow time scale such that the reaction zone can instantaneously adjust to whatever happens. So you can say that SL equals SL phi quasi-steady, SL of local phi quasi-steady.
Okay, right.
But we discussed this in that paper by Sri Krishna, where we say that if you don't have this, how to model this, we've discussed that as well.
Yeah, but there is a lot of studies which says that kinetics plays an important role, and
I'm not
heat release will be, when you calculate it from burning velocity from the heat release, then those things matter much.
Well, we can discuss this.
How did you arrive at these 14% equivalence ratio fluctuations or variations, or 60% of the mean? What is the basis for coming up with these?
Well, currently this was just an academic study. Okay. So I didn't try to go in to look at what might happen, but with talking to people, I was told that up to 30% is not uncommon.
It depends on what is the mean equivalence ratio that you are actually parking, and
yeah.
what is the frequencies that you are interested in.
Yeah, so, absolutely.
Okay. The second question is, you did a lot of all of it was fuel side perturbation.
Yeah.
Have you done anything with air side perturbation?
I didn't, because my aim in this study was to validate the model.
Correct, but you didn't show that.
Yeah, no. All I haven't done. I didn't show any air side perturbation result, but the model by itself can do air side perturbation. You can do both.
When you did air side, if you have done air side perturbation, what was the variation? Did you actually again go to 15% equivalence ratio?
No, we haven't. Okay, I understand what you're saying. I mean, I haven't looked at perturbing the airflow at all, because if I did that, then I would essentially it would be equivalent to perturbing the fuel flow in my case, because I'm keeping the inlet mass flow rate constant. And the reason I'm doing that is because I just want to validate the response of validate the model just for phi alone, without introducing U fluctuations. But the model as set up, the framework itself allows for both things. But whether we have done coupled simulations, that's something that's in progress. Yeah. The DNS would take care of it, and for the reduced order model, there would be a significant effect if you took care of it. Only you can estimate it from the theory, and that's for the parameters of this simulation, it would be important only for greater than 300 hertz. So which means about 80% of those points would not change. The model prediction for 80% of the points would not be significantly different, even if I took it in.
So we once again thank Dr. Hemachandra for his presentation.
Thank you again. It's been I guess a very long but productive day. We have a couple of quick announcements. We are set up for a group picture right outside on the steps of at the main foyer, at the main entrance. We'll assemble there for that. We'll have transportation right outside again in the main foyer to the cultural program this evening. That is to start at 6:30 p.m. on campus, which is technically right across the street. But if you want to walk, it's about a 15-minute walk. But we'll have ride here that we can go watch the cultural program. Thank you again very much.